Our speaker today is John Dickinson. He's the Director of Technology at SwiftStack, and Technical Lead of OpenStack Swift.
Thank you. As he said, my name is John Dickinson. I work for a company called SwiftStack. We focus on the open source projects called Swift, part of the OpenStack project. And today, I want to tell you a little bit about why I think that Swift, and specifically with OpenStack and other open systems like that, are very important to me, why I think that they are going to change the world and we're all going to be a part of that. And also, there's lots of information about there, and I've spoken this week already about what Swift is and kind of how it's put together and how things work. But the second part of this talk, the majority of this talk, we're going to go through and actually test to destruction a Swift cluster, so to speak, and see what happens in different failure scenarios and how Swift recovers from those. So to start with, a very, very high-level intro, what is Swift? I think it is the evolution of storage. It is the future. Swift is a large-scale distributed object storage system. It's built for scale, it's optimized for durability, availability, and concurrency. And it is conceptually similar to something like Amazon S3. And so it is good for any kind of unstructured content that can grow without bound. It's been running in scale in production for several years. I've been working on Swift for about 3.5 years now. Since it started at Rackspace and then now as part of OpenStack in the overall community. So to start with, why is this important? We can all talk about what the code actually does and what problems we're trying to solve very specifically and how we solve those, but taking that up one level into the why of things. The reality that this is my soapbox here, that everybody has data. And it may just be cat pictures, but in more seriousness, companies and individuals have all kinds of data. We've got everything from videos to user data, static websites, backups, things that are large-scale data sets used for scientific purposes, research. It's been a huge thing I've heard this week with people like Nectar and some of the university research here. And yes, it may include some cat pictures. But the reality is that data is always growing. It's the fundamental thing about data. It's always getting more. We've always got more of it. And so we need to figure out how to store that effectively, because there's 3 things that you can do with data. You can either compute on it, you can store it, or you can move it around. And storage, I believe, is key, because that's the foundation that you're going to build your computing and your networking on. You have to store something before you can transform it or move it to someplace else. So we have to get that right. And something that I've heard from, sorry about that. Something that I've heard actually from some people who live here, and Tristan Good, the CEO of Aptera, phrase that I got from him is data sovereignty. And this is something that is incredibly important for people all over the world. And specifically this week, talk about how it's important in a place like Australia. There are certain government laws and things you can and can't do with data for certain industries. You also want to be able to have ownership of your data and things that touch your data. This is for me is the why of open systems. This is what it all comes down to. It's ownership of your data. That doesn't necessarily mean direct control. You may choose to offload some of that to a hosting provider or something like that. But the reality is you need to have control over your data. You need to be able to have ownership over everything that touches your data, from the hardware to the software running on that hardware, all the way down to your tool chain on how you're accessing your data. And it's open systems that make this possible. Because in communities like OpenStack and the Open Compute project on the hardware side, and even looking at why we're here this week with Linux, you have not only the ability to influence the actual code and add features and patch bugs and things like that, which is great, but you have the ability to control the entire community around those things. So it's not only the fact that you can get the source code, but it's the fact that you can actually push that forward and the whole community forward and influence that community itself. And I think this just comes down to the original 4 freedoms of the free software movement. So my vision for Swift is that everyone, every day, will use Swift whether they realize it or not. And this is just some of the companies that have contributed to or announced that they're running Swift. A lot of hosting providers, they have tens of thousands of customers. You've also got other people who are doing things like storing videos and web images. The point is, when your mom picks up her smartphone and starts playing games, I want her to be using Swift. When you go help your kids with their homework and go look up something on Wikipedia, I want them to use Swift. When you're logging into your bank records and figure out, looking at old images of your bank statements, these are all amazing use cases for something like Swift. And that's my vision, that it will be the storage system that is underlying our day-to-day lives. So that's my introduction of why I think this is important and what really is exciting me about being a part of OpenStack, Open Compute, and overall open systems and contributing to that. I would love to have you come join and contribute to that. We've got an open system of contributing code to Swift, and so please join. So now, let's get into playing with Swift. There are 2 hard problems to solve in a distributed storage system. The first one is figuring out how to place your data within the cluster, make effective use of your machines, and isolating particular pieces of data to protect against failures. And the second hard thing to do in a storage system is to protect against data failure, or hard drive failure, hardware failures in general. And so in a cluster of any size, hardware failure is inevitable. So you have to figure out not if it happens, but what do you do when it happens. So there's 4 things I want to cover. The first one is 4 things we're going to look at. We're going to look at what happens when a hard drive dies, what happens when a server dies, what happens when a hard drive gets full, and what do you do about bit rot on your drive. So first off, this is where we're going to start switching back and forth. And as a matter of intro, I've got a virtual machine running on my laptop that has 4 Swift simulated Swift servers. It's got 4 instances of each of the pieces of Swift, and each using 1 hard drive. And so we're going to do things like unmount hard drives and kill things while it's running and then see what happens. So first off, look at the happy path. If we're looking at a basic GET request, see what happens there. Let's do that. So I have a couple things open here. First off, we've got what are we doing here? Okay, let's reset Swift. We've got everything working. And we're going to start the main servers. We're not starting the background consistency processes yet because otherwise it would recover too quickly and we wouldn't be able to actually see what happens. So we've got that running. I have that's a different window. So I'm looking at the Swift logs to see what happens over here. This is where we're going to see what happens. Now, we're going to grab a token from the cluster. We can do a request there, and you can see that we've got some requests coming on there. So now let's do create a container. Just as a clarity here, this part of my request is just kind of the prefix of a URL, just the IP I'm talking to, v1 for the API. This is my Swift account string, auth ABC. I'm going to create container C, and you can see that was created. And now I'm going to got our things there. And now I'm going to create object O, and we're going to say that's going to be data binary 1, 2, 3, 4. So there we've got our request, and you can see here a few important things. In here we did a head request on a container, and more specifically what I'm looking for is we've got object server, and object server. Each had a put request that was successful, which caused the proxy server to return, with the put request here, to return a successful response code of 201. So this is the happy path. Everything was just fine. And we can verify that by looking at, and on disk, here are the 3 copies of my data. I'm looking in my root directory where my hard drives are mounted, and you can see now that I've got 3 copies of my data, these data files here. They're named by their hash and the timestamp. So now let's move on, now that we've seen that. So we're going to cover these 4 things. So first, let's look at bit rot. Here's what we're going to do. We're going to put an object. We just did that. Now we're going to corrupt the object. And to corrupt the object, what we're going to do is just echo a string into that actual data file. Then we're going to trigger the auditing background process, turn that on, and see that it gets moved out of the way. And then we're going to turn on the replication process and see that a good copy gets put back. Should be pretty straightforward here. OK, so you can see here that I've got these 3 copies of this one good data on disk. So let's go into the first part. You can see I've got a copy in D1. So let's go into D1, objects, and here's the actual file on disk. If we cat that out, you can see that the data is right there, the 1, 2, 3, 4. And we can look at Swift object info for that file and see that it was in this, this account, this container. The object name is O. Here's the hash of it, where it should be, otherwise in the cluster, some of the metadata. And specifically, the e-tag here is valid. The hash of the data on disk matches the hash that we're storing. So now let's have some bit rot. Echo evil into my file. That was pretty easy. Now, if we cat the file out, you see that I've got evil data in it. And if I look at the Swift object info, you can now see that the content length doesn't match and the e-tag is invalid. So, in that case now, let's trigger the object auditor.
Can you just flip back to that one where you showed the tag?
Yes, here we go. So the e-tag is different. It does not match the file hash. So the actual checksum of this is stored in the extended attributes of this file. We didn't update that. We didn't corrupt that. So assuming we had a file system or hard drive corruption in this case, the e-tag is not going to match. So now let's start the object auditor. Switch over here, and very quickly you can see that it scans the directory tree there, and now we've got 1 in objects, 2nd in objects, and in D1 it now got moved into quarantines, and it's no longer available there. Now we're still going to be able to access this data with no problem because we've still got two copies in the right place. In the meanwhile, on a production Swift cluster, of course, you are going to have the object replicator run. So in this case, we start the object replicator, and you can see that that one of the good copies was pushed back onto the other copy, and things are good to go. The quarantined object still stays there, but now we still have our full durability guarantees of 3 replicas in our cluster, and things are good to go. So that's how Swift protects against bit rot. If you look back at the data on disk, we can look at the Swift object info, and oh, that's because if we look back go back into the drive instead of the cached items. So we look back in here and do Swift object info. You can see that it is now valid. So we've now protected against bit rot. So number 2. What happens when you have a hard drive down? This is the most common failure within any sort of storage cluster. Hard drives fail all the time. So we need to actually make sure that that is protected. So what we're going to do is we're going to find out one of these locations. In fact, we can kind of skip this step. We know we have an object. We know where it's going to be. So we're going to kill one of those drives. We're going to unmount drive D1. Then we're going to put an object in there. and see what happens, see where it goes with our durability guarantees and things like that. Then we're going to turn on the replication process and see what happens as far as rebalancing the data once, and then we can even bring the drive back up and see what happens. So we're going to start again with reset Swift. This reset Swift script basically kills everything, unmounts my hard drives, reformats them all, and just basically starts completely from scratch. What you can see from my find command that's running here is there's no data. Turn back on logging again. And now I need to get my token. We're going to put in container C. Now let's put in object O. You know what? I shouldn't have done that, should I? Oh, actually, that was fine. Sorry about that. Let's do that sequence all over again. Okay. Now, the reason I have to get a new demo token every time is because I'm killing memcache, which means that my previous auth token is not valid since I've started everything all over again. And so I need to get a new one. Okay, now we're going to put this object in there. We still have all of our drives up, so that's going to be fine. Okay, so now we have our drives. We're good to go. So in this case, let's unmount my drive. And if you look here, you can see that we do not have our drives mounted, and I only have 2 copies of my data. In this case, now let's trigger replication. In this case, we can see we got a 3rd copy that came right back up. Swift will automatically detect when your hard drive is bad, will automatically unmount it, and then in that case, when it detects an unmounted drive, it will ensure that you have a 3rd copy somewhere else on a handoff node. So here you can see that I have a 3rd copy. Instead of on drive 1, I've now got it on drive 4. This is not the primary location, but it still guarantees my durability of my data long term. Now, what happens if so we've got replication running, that's fine, we don't need to stop that. But what happens if I re-put something with the same object name? So it's supposed to go onto that primary location again. But I'm gonna overwrite the object, and it's gonna be 1, 2, 3, 4, 5 now. And get some white space on my log. It's gonna try to put it onto drive 1, which is unmounted. I still got a success. And what you can see here is that lots of things happened. Oh, that's the replication log. What happens is that the object was put, and where did that go? Object replicator, that was chatty. Here we go. When the object was put, we got a handoff node that was requested. And so that, that primary location was not found, and it pushed it to a handoff. 1, 2, 3, 4, 5 exist in all of these places. And if we really wanted to verify that, we can cat the data out for that handoff location and see that it is 1, 2, 3, 4, 5. So there we go. Now, if we mount our data again, mount the drive. So to mount this drive again, I'm mounting it by the label, mounting as an XFS partition. And then we watch to see what happens here. You can see that that was resurrected, and we've now got it available. So replication is running on the back end, and shortly, what will happen is that the good copy will come back, and we will see the copy off of D4, the copy on D4, go away. So what happens is all of the D2, D3, and D4 are all actively performing replication processes. It happened. And then they are pushing it to make sure that it is in the primary locations overall. And in the case of D4, that simulated number 4 object server, it detects that the primary locations are completely outside of itself. So once it has successfully pushed it to all of those things and make sure there's good data, it will delete it locally. And therefore, we'll back down to our 3 replicas and things are OK. So that is how Swift automatically handles drives being down. So next thing, one level up. What happens when you have a server down? This is not as common, but it is distinctly different. Oh, we're at the Linux conference, so let's use a sad tux. So in this case, things are a little bit different. Drives down is not that big of a deal because today you're losing up to about 4 terabytes of data. What happens when you have 34 terabyte drives plugged into one power supply and your power supply dies? You don't want to automatically start replicating all of this massive amount of data across your switches. That's going to saturate your networks. You're going to have big problems. Not only that, your data is not really gone. It's just unavailable right now. So that's the assumption that Swift makes. When you have a server down, in other words, you cannot connect to a particular server, Swift will not automatically trigger replication on that server. It simply assumes you have a temporary availability issue that will be resolved by some operational input, like fixing your power supply or you're plugging your network cable back in. So in this case, we're going to put an object, then we're going to kill one of those servers. We're going to then put another one of those objects and see where that goes. And then we'll bring the server back up and see how things work. So let's demo that. So first off, we will reset the Swift environment. And then we will start the primary processes. Here we go. So we're going to get a demo token again. We're going to create the container, and then we will create the object inside of that. Great. Now you can see we have our object again. Make sure our logging is working again. And now, let's see, now we're going to kill the object server. So you can see here we've got 3 parent processes and 3 child processes. Specifically, I'm looking for the ones that are using number 1. So we've got these two kids here. So I'm going to kill 9018 and 8948. So we should have only 3 object servers running right now, one of which is the primary location for our object. We still show 3 here because this is kind of all simulated in one environment. So just for completeness, we will also U-mount that drive because in a real world, if your server's down, obviously you can't access those drives. So now we have this. So let's put another object. Okay. Now we're going to put object 02 and see what happens. Okay. In this case, you can see that we have object 02 on, we've got an object on D2, another object on D2, D3, D3, and D4. So we've got at least one object on, here's our first object, you can see by this hash here, the 827 hash. And then EFD hash is here, here, and here. So we've got 3 copies on one and 2 copies of the other. In this case, we have, you can see that there was a handoff requested for that object. And so we still put, for new objects, we still put a full 3 replicas. But we only have 2 replicas of that one that has that temporary unavailability. If we mounted the drive and launched the server again, we're still going to be there. So let's do that. In this case, I'm simply going to Swift init object server restart, which will kill all three of them, and, well, kill both of them and then start all three of them. And then we need to mount the drive again. I think that should work just fine. And now you can see we have the full 6 copies. If, for example, we would have updated the first object, then replication, we would have an out-of-date copy on the drive that just came back. Replication, of course, would have detected that, hey, you have a newer copy over here. Replication would participate in that. And in this way, when a server goes down, a complete server goes down, it's generally just a temporary failure, and you haven't actually physically lost all of your data. So that is not considered a durability loss, but just an availability loss. Swift will continue to work around that. All new content will continue to have three copies. And then when that server comes back, you have your full availability again. So moving back. Next error. What happens when we have a full drive? In this case, just because it was the defaults and I was just clicking enter, 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 enter when I was setting up my VirtualBox, each of these drives are 8 gigabytes. So what happens if I try to upload a 100 megabyte object into the cluster, but I've already DD'd 8 gigabytes onto the drive? What do we do? So let's do that. The general rule with the storage system, of course, is that don't let your hard drives get full, right? Because it's a storage system. That's what it's supposed to do. And of course, this is the cloud storage system, so it's infinite, right? If you don't believe me, just ask the marketing guys. The reality, though, is that at some point, you're probably going to run out of hard drive space accidentally. You hope that doesn't happen, but it is a use case that has to be taken into account. You have to actually be able to handle this sort of error condition and not, say, start returning errors to your clients, or worse, just crash. That would be bad. So let's clear out everything we have. Start from a clean environment. And you can see here that if we do df-h, I have my 4 8 gigabyte devices with only 1% used. At this point, I have, whoops, where is that? Ah, yeah. Here's my DD commands. Copy just a bunch of zeros. Unfortunately, I can't use something like truncate because it doesn't actually write the data to the disk. So here, writing 8 gigabytes. While we're doing this, I'll show you this. I have a 100 megabyte file on this, on locally, and that is what I'm going to now try to upload. So you can see I tried to write my file, everything was good, but, well, I did what I was supposed to. I was trying to actually, wait, what? Awesome. That wasn't intended. Yeah, I was supposed to be in serve node D1. I've heard that DD is a fantastic, the acronym it actually stands for is Disk Destroyer. So apparently I just did that. Anyway, okay, now we're going to fill up the right drive and see what happens. So while I'm doing that, I will go ahead and get my demo token. Everything you can see is still just fine here. We're going to export that drive. Now, if you're not familiar with curl, there is a -t, which takes a local file and will upload it as the body. Okay. We now have drive number 1 is full of 8 gigabytes. So there's no possible way I can write 100 gigabytes onto this, 100 megabytes onto this full drive. So let's see what happens. We're going to pay attention to the logs in this window here. And here we go. That's funny, it worked. And we've got 3 copies. Notice it's on D2, D3, and D4, not it went to D4 rather than the primary location of D1. To explain how this works, notice this line right here. There's a part of the HTTP spec which is somewhat rarely used, I think, and it is fairly convenient. When you are uploading something, you can send an expect 100 continue header. What this tells the server is that if everything is okay by the time you get all of the headers, but not before you've read the body, if you think you can actually accept this request, just if you can make a determination, go ahead and send me back a response code of 100 continue. At that point, I know that it's safe for me to throw all these bytes on the wire. That means that, for example, in this case, if 100 megabytes were not able to be read, then I don't have to read 99 megabytes, figure out, oh no, I'm out of space, and then only at that point deny the request. If you look at the logs here, when the request was received, you can see that there was, where is it? This request right here, this object server, got the put request, but returned with a 507. 507, when it gets the expect 100 continue response, the object server looks at the content length that was sent as part of the header, and then will try to f-allocate space on the drive. F-allocate guarantees that if it returns successfully, you will be able to write that many bytes without getting a partition full error. So in this case, f-allocate failed. So therefore, the object server returns a 507, which is the standard HTTP response code of entity too large, I think, or out of space, basically. So the proxy server then chose a handoff location and sent it to D4. And therefore, in this case, you can see that there was there's a total of 1, 2, 3, and 3 more successful put requests that all were correct. And therefore, the proxy server down here was able to successfully return with a 201. Now, let's start. That. Swift init object replicator start. This is going to start looking on the drive and make sure things are in the right place. Of course, we can't move anything back to that one full drive because it's full. Unless we go to D1, you can see that we've got our big file there, so let's remove big. Now we have plenty of space on that drive. And let's see what happens. This is going to be fun. So specifically look at D4 right here. What's going to happen, let's see how fast it happens actually. Aha, now we've got 4 copies because that 100 megabyte file was copied from D4 or one of the other ones to D1 into the primary location. D4 still needs to detect that it actually is successfully put on all of the other 4 servers, and then it can delete itself. So that is what we will see right here. In just a moment. This is actually running with I think a sleep of 30 seconds. So it shouldn't take more than about 30 seconds. There we go. And now we're back down to our full replication count, or our original durability guarantees, 3 replicas in the cluster, and everything is just fine. And that's it. If you have more questions about Swift specifically, you can grab our source code off of GitHub, the OpenStack account /Swift. You can find some of the some good docs at swift.openstack.org. IRC is the OpenStack channel on Freenode. I work for a company called SwiftStack. We have a lot of great Swift documentation, including lots of blog posts and videos about how Swift works and things like this. In fact, I'm currently writing this up as a blog post. I am not my name on IRC and Twitter and other places. What questions do you have? Okay.
Where does the metadata live that actually connects your objects with their names in the Swift namespace?
Okay. That lives in a data structure called the ring. And the ring is a, let's see. When The location is taken from the hash of the object name. So the account, the container, and the object. And then the first few bytes of that hash end up becoming a partition of the overall key space. Each of those partitions then are mapped to a storage volume. So there is a deterministic mapping based on the object name, the hash of the object name, so that anybody who has a copy of this ring mapping will then be able to take any arbitrary name, calculate a hash on it, and look up exactly where it should live in the cluster. And that is how that happens. The other metadata, things like the content type, the checksum on the actual contents of the data, and things like that, live in the extended attributes of the file. That's actually a very long and detailed topic. There's lots of information on there. I'd be happy to talk to you more about it. But basically, it's a deterministic mapping from the hash of the ring name.
Right. It can't get lost, corrupted, or run out of
Absolutely.
space or anything
Yeah,
like that.
you can't lose that. It's math.
Yep.
Why does D1 need to get a copy back originally? Why do you have this idea of a master location? Like once D4 had a copy of, well, in two examples you showed, you had your durability guarantee.
Right. That is a great question. So let's look at that a little bit. There's a tool in Swift called Swift Get Nodes. It tells you lots of information about stuff. So we're going to load the object rings, is that data structure file, that mapping. And we're going to look up auth ABC containers C object O, which is, you can see, the object that we were putting here. It's just the components of the path here. Once we do that, you can see that here's the pieces of it. This is the partition it lives in, the hash of the data, and the primary servers that it lives on with the IP port and mount point, and then the handoff node, and then some helpful copy-paste tools to get to that. The reason that we need to put it back on the primary location is because read requests only look in primary locations. They will look in one of those three locations. You will have as many potential handoff nodes as you have actual storage volumes in your entire cluster, which makes sense that then for writes, you can continue to try to put it on new drives in the cluster because you really want to get a copy of that data there. The problem is, if you have a request that doesn't exist, it could just be mistyped or something that is on the handoff nodes, it's kind of indistinguishable there. You do not want to start making requests to every single mount point in your entire cluster. It's very hard when you have tens of thousands of drives. And so it will only look at the primary locations, in which case you want to ensure that your data actually lives in the primary locations. The second reason for this is because the primary locations are chosen so that all of the drives will fill up evenly. And you don't want something to, based on a hard drive filling up, some sort of cascading failure scenario that one drive gets disproportionately full, which then fails over the others and things like that. It's going to make sure things are evenly balanced throughout the cluster.
Also, because one of the disks may be in another data center?
One of the disks may be in another data center. Not today, but we're working on that. Let's just say, yes, it could be far, like network-wise, farther.
Well, in general, I agree with you that object store is likely to be the future of storage. Block device storage is still required by a bunch of applications, operating systems, etc. So the question is, do you have plans to introduce block device storage in Swift, and when?
No, we have no plans to introduce block device storage into Swift. We believe that is a different use case solved by a different storage system, and that each storage system should do that thing well.
So for your setup, you always need a spare fourth node.
No. If you want any sort of HA, you always need a spare node. So I could have run this actually with just 2 nodes. Because I've got 3 replicas, success is determined, of writes is determined by quorum. So two writes had to succeed. If I went with only 3 nodes, I can still have my full durability guarantees. Unfortunately, then, I would not be able to have handoff locations in the case of a failure. So in this way, this is one of the ways that Swift is more resilient to failures the more it grows. The bigger you have a cluster, the better able it is to handle failures. A production system should have at least replica count plus 1 storage volumes, but that ends up being at minimum 4 hard drives, which is pretty small.
How do you compare the Swift and Apache's Hadoop file system, if they have any overlap?
How do I compare Swift with HDFS? I don't think there's a lot of overlap there. HDFS is a file system, and Swift is not a file system. It's not, you can't mount it, it's not POSIX, it's not a file system. HDFS is designed to go really fast and assume that jobs can, it's okay if things get lost, things like that. Swift is designed for more durable storage. Hadoop is designed for let's mutate some data very, very quickly and in a distributed manner. That being said, I do know of some use cases where people are using Swift clusters as the source of the data they're putting into Hadoop, and then the destination of the data, of their mutated data they're getting out of Hadoop. So I think they're complementary, but they don't overlap.
Is there anything in the conceptual design of Swift that would make it hard to add a block device layer on top of it? So if you guys are not doing this and other people want to do this, is there anything in the conceptual design that would make it really hard?
I think probably yes, because Swift is, if you look at the CAP theorem, saying that you can either you can pick two of consistency, availability, or partition tolerance, network partition tolerance. Swift sacrifices consistency, which generally becomes extremely important in use cases involving block devices. Inconsistent block devices are generally a non-starter. And